All right, we now have reached the most important part of this section, which is Theorem 9899. And I need you to slow down for a second. I need you to be careful with what these two theorems tell you, and more importantly, in my opinion, what they do not tell you. So we have to not be sloppy in our thinking, and which is, again, I am just as guilty as anyone, especially when I'm tired. But we want to slow down, and we really truly want to understand what these theorems actually tell us and what they do not tell us. And I'm going to start with a little bit of geometry to see if I can help make sense of the theorems. So notice that I have n running along that x-axis. We're going to label that that x-axis. We'll say it's n. And what we have is we have a few points indicated here. And what I want to do is I'm just trying to give you a visual. It doesn't have to match. It doesn't have to match what this theorem is saying perfectly. I just want to give you a visual that if you think about, if you plug 1 in for n, this would be your point on your y-axis. All right. Well, if you plug in 2 for n, this would be your point on the y-axis. And I want you to think about this amount here as the so y definitely decreased, right, as you went from A to B. But the amount that it decreased from A to B, let's then look at the amount it decreased as you went from B to C, or the amount that you decreased as you went from C to D. Do you see how that amount that it's decreasing, or you could even think the amount that it's increasing, that is getting smaller and smaller and smaller as you move away from the origin, as n goes to infinity. Now, that just that little bit of geometry in mind, let me see if I can read this very first theorem. Right, this is the limit of the nth term of, that's very important, of a convergent series. So notice it's an if-then statement, right? It's a conditional statement, and we start off with the if, right? This is what we assume. We assume that some series converges, right? So we start with that assumption, if some series converges. Then the conclusion is the limit as n approaches infinity of a sub n must equal 0. And that's, so with that, you would think about it as you start to list a sub 1, a sub 2, a sub 3, right? These are terms of the sequence. And then you start to list your partial terms, s sub 1, s sub 2, s sub 3. But the idea is that the amount that you're adding, right, as you get to a sub 1 plus a sub 2 to get to here, then a sub 1 plus a sub 2 plus a sub 3 to get to here, that amount that you're adding every time should, every time, it should be itself decreasing. I mean, if I just keep giving you more money, like if I give you $1 today and $2 tomorrow and $3 the next day, and if that amount is just continually increasing, then we would never talk about the sum as the days go to infinity approaches some finite number, right? We would think about it as in the limit, and that would be going to infinity as well. The sum would be going to infinity as well as. But if the amount that I give you every day, every other day, is itself decreasing, right? I give you 50 cents, then tomorrow I give you a quarter, and the next day I can, and so forth. Then that's what they mean by the limit of a sub n is approaching 0. This here is approaching 0. Okay. Now that is what the theorem tells us. If it converges, then in the limit as n goes to infinity, a sub n is 0. Now, what does it not tell you? So what if we know that the limit as n approaches infinity of a sub n is 0, right? What if we know this? Then what can we say about convergence or divergence? Nothing. You do not get to switch your if-then statements around, right? You have to if you say if the grass is wet, then it's rainy outside. You don't get to switch that around and say if it's or I should say it the other way. If it's rainy outside, then the grass is wet. You don't get to switch that around and say that if the grass is wet, then it's rainy outside, right? Because that's not necessarily true, right? It also could have a sprinkler on. That's why the grass is wet. Do you understand that you don't get to just switch your if-then statements? So, in other words, if you know that it converges before you start, then you will know that the limit as n goes to infinity of a sub n is 0. That is the idea. Now, the more useful theorem is going to be this nth term test for divergence, because think about it. A lot of times you're not going to know that it converges from the beginning, right? You're not going to know that. So then notice that this next theorem makes a statement about if. Now, it doesn't say anything about if the limit of the general term as n approaches infinity equals 0. That is not said anywhere here. But they said, look, if the limit as n approaches infinity of a sub n does not equal 0, then you get to make a statement that the series diverges, right? If this is not true, right, if the limit as a sub n does not approach 0 as n goes to infinity, then that is helpful for be able to make a statement about the divergence of a series. It diverges. The series, it's an infinite sum, but it diverges, means it's just going to go to infinity or negative infinity or so forth. So let's just, I hope that those explanations were helpful. Let's go ahead and just practice a few real quick. So it says for the following series, let's see if we can use those theorems. So notice that it does not. Okay, really quickly, does it tell you this converges or this converges or this converges? Does it state that anywhere? No. Then you can't use theorem 9.8 because that says if it converges. Right? In fact, what we're looking for is does it converge or diverge? So if it converges, we already have the answer to the question. And no, instead, we're going to use the second theorem. And so we want to take the limit as n approaches infinity of 2 to the n. All right, and now look. If this equals anything else than 0. If it equals anything else other than 0, we get to say it diverges. That's what that theorem says. Well, look, 2 to the n as n approaches infinity, this is equal to, does that equal 0? That's the only, does that not equal 0? Yes, it does. It does not equal 0. So we get to automatically say diverges. Okay, let's try another one. So if it equals anything else than 0, more importantly, it should say if it does not equal 0, then it diverges. All right, let's look at this next one. For the next series, now all I'm going to do is, because I want to be able to take the limit of that, is letting n go to infinity. I'm going to go ahead and right now I would get infinity over infinity if I took the limit. So you can think about it as this is a factorial, so I'm going to divide the top and the bottom by n factorial. Right, we can use some algebraic techniques here. So that would n factorial divided by n factorial is 1. 2n factorial divided by n factorial is what? It's just 2. And then it's just plus 1 over n factorial. Okay. Now we evaluate the limit. So this is going to go to 0 as n goes to infinity. So we end up with 1/2. All right. 1/2. If the limit as n goes to infinity of a sub n does not equal 0, right, and this does not equal 0, then it diverges. So that does not equal 0, so we get to make a statement diverges. And now we'll find out if you were listening to me. So, looking at the series, now we're dealing with 1 over n. We'll figure, like I was saying, we'll find out right now if you were actually listening to what I was saying earlier. So if we take the limit as n approaches infinity of 1 over n, well, that's just, if you got $1 and you chop it up an infinite amount of ways, nobody gets anything. So this equals 0. So if the limit as n approaches infinity does not equal 0, then it diverges. Well, hey, this equals 0. So what do we get to say? What do we get to say about this? That it converges? No. We cannot, there's nothing we can say. It's not the test itself. The test is built for when it does not equal 0. The test is not built for what happens if it equals 0. If it equals 0, that doesn't necessitate convergence. If it is convergence, it's necessarily that the limit of a sub n as n approaches infinity equals 0. But not, you don't get to just take a test and switch your if-then statements around. Okay, everything has to be proven in mathematics. Those are called biconditional statements. If you can take what comes after if and what comes after then, if you can switch them around and you still have a true statement, then that's biconditional. But these are conditionals, so you don't get to do that unless so. This is there's what do we get? What is the answer? Well, there's nothing you can say. There's not enough information. You can't use this test. You need another test. All right. See you in the next section.